Okay, let me share my screen. Can you see my screen, please?
Yes, sir. Yes, we can see your screen.
Oh, okay. Thank you, Emmanuel. So let's start. As I said, this is just like a short tutorial on feature engineering that I'm sure most of you already know because you have been doing feature engineering, even if you don't know that you have been doing feature engineering, because you cannot just do data analysis without doing feature engineering. So feature engineering is basically like the different operations you just perform on your features to make them fit for for your algorithms, for your model, because there's some kind of work that you are supposed to do before you think of any statistical modeling or machine learning modeling. So this is just basically feature engineering. So the operations that you are performing on the features, right? Like scaling, encoding, like transforming features, constructing features, feature reduction. So we in this tutorial we're gonna cover like few of them. We cannot just cover everything, but we're gonna talk about feature transformation, feature. I'm sorry, I have to admit people at the same time. So okay, so we're gonna talk about feature transformation, feature construction, and feature reduction for this tutorial, right? Okay, let us start with feature transformation. In future transformation, sometimes, for example, let me give you an example which is distributed, and that to fit the model, which requires the data to distribute work better. So forming the data is just like some functions on data on the variables that you are interested in order to it like nice, like just make data or variable to be come again, please.
We can't hear
Hello.
you. Your network is breaking. We can't hear you.
Oh, you cannot hear. Can you hear me now?
Yes, 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 yes.
Oh, I'm sorry. Right. Okay. I was saying that like future transformation is like you are just applying some kind of functions to your data or the variables that you are interested in to make it like, okay, let's say that your variable is not normally distributed and you want to fit a linear regression model, which mostly requires for your variables to be normally distributed. So you just plot the histogram of the data and you realize that the data is not normally distributed. So then you apply some transformation functions like the log transformation or the like square root transformation that we're going to discuss here to make it normal. Okay, let us just see some examples. Here I have loaded the car sales data, and then let's say that I want to like fit a linear regression on the the column sal, like the sal columns, like the sal in thousand, the sal columns here, which is a continuous, for example, variables. Okay, first of all, I have plotted the histogram of that variables. You realize that the data is rightly skewed, right? Is here. The data is rightly skewed. So, okay, the best way before, like, ideally, before you fit the model, it's better to try to make this more like to looks like to be more normally distributed. Okay, because if you just fit the data like this, okay, just think it as the same way that if you have unbalanced data, right? Your model may pretend to be a very good model, and that's not the case because the model is like the data is skewed to the left or is skewed to the right. Okay, so this is what happened here. Okay, and this is why we need some kind of transformation. Okay, that's why we call it feature transformation. We have to transform this feature before fitting the model, for example. Okay, and you can know exactly the value of the skewness, for example, which is like 3 point something, which is heavily skewed to the right. Okay, so to make this more like to looks like to be normally distributed, we have to apply some functions, and among them there is what we call log transformation. Okay, which makes the data to be like somehow normally distributed. Okay, which is very easy here. You just have to use this function numpy.log. Okay, and then you specify the variables. Here we are interested in this variables, sal variables, and then when you apply this function, you plot again the histogram of the variables. You see the difference. Now it's better, you know. Now it's better. It's like we have some kind of like the normal shape, like the data is somehow normally distributed comparing to this first one. You see what I mean? So this is like future transformation. You check your data, you plot the histogram of your data, you realize that the data is skewed. Okay, before you fit the model, you have to transform the data, right? You have to transform the data by using, for example, different kind of transformation functions. Here we have used the log transformation functions, which makes the variable to be more normally distributed. There is another one also called square root transformation. Okay, this is the same, like we have the same thing, like the idea behind these are the same, is the same. For example, it's just to make the variables, the data more normally distributed. Okay, here we use just numpy.sqrt, and then you specify the variables, and then you see now you like at least it's better, like when you compare it with this one. So it's up to you. There are so many other like ways of doing this feature transformation by using other functions, you know. So but the idea is just whenever you have, or whenever you want to like fit a model, let's say you want to fit a linear regression model, so try to check if like the data is somehow normally distributed. If not, you can use these transformation functions to make it more normally distributed before then you fit the model. So basically this is like feature transformation, which is very simple to understand. The other thing is in this feature engineering is scaling, that you already know, right? Okay, because it is always a good idea to scale numerical descriptive features before fitting any model. For example, if you have a numerical features, so it's always a good idea to fit, like to scale your model, because the values might be like very far from each other, you know. So try to like put them like to be very close to something that like you anymore have that gap, for example. So anytime you have a numerical features, try to scale those numerical features before you fit your model, for example. Okay, and mainly we have min, max, scalar, and standardization. So I'm sure you have been using this in your past assignment, or maybe.
Elijah, you have a question.
Okay, go ahead.
And check the chat, but I think someone sent a message.
Which one?
I said you can check the chat box. Chat
Oh,
box.
okay. Oh, okay. Sorry. Okay. Oleshua, you are asking what is the point of the data to be normally distributed before fitting it to the model, right? Okay. So if I understand your question, why do we need to make the data to be more to be normally distributed, right? Okay. So as I was, for example, let's see this variable. Okay, just think it in the same way, like if you had unbalanced data, for example. So this data is rightly skewed. Okay, and we know that if the data, if the variable or if the data is normally distributed, we have a symmetry. For example, anytime you fit a model, like the bias will not be like that much when you fit the model without making it to be normally distributed. For example, because the data here is on one side. For example, let's say the data is on one side. If you just train the model here, the model will just learn on one side. For example, just think it as the same way if you had unbalanced data, for example. So, but if you have the data to be normally distributed, it's symmetric. Like whatever you have on the left is like not very far from whatever you have on the right. Okay, so, and for example, a model like linear regression model, it requires for the numerical features to be like normally distributed. Anytime you have a feature like that and you realize that the data is heavily skewed, so it's always like you should always try to make this normally distributed, for example, by using this transformation function. So it's just to make your model to be less biased, for example, because if the data is just on one side, I think the model, it might give you a very good performance, accuracy, thinking that you have a very good model, but it's biased because the data is on one side, right? So that's what I mean. I don't know if I have answered your question. Okay, thank you. All right. So here I was just talking about scaling. Okay, so it's always a good idea if you have numerical features to try to scale them, because as I was saying, like sometimes the data or the values that you have within your variables, they might be like very far from each other, right? For example, you have student max, you know, there are some 1/20 and then some 18/20, something like that. So these values are very, very far from each other. So it's always a good idea to try to scale those values to make them like closer, right? And the main methods here we are using, and you have been using it, I'm sure, for the past challenges or even for these challenges. Okay, min max scalar, each in this method, I'm sorry, in this method, each descriptive features is scaled to be between 0 and 1. Okay, now after you use this method, for example, whatever you have as value in these variables, it will be between 0 and 1. It won't go like you cannot have something less than 0, and you can also have something more than 1. And you realize that now the difference is not that much big. So, okay, or you use the standardization one. For this one, each descriptive features is done via standardization. What I mean, so each value of the descriptive features is scaled by removing the mean and dividing by the standard deviation of the features. So this ensures that after scaling, each descriptive features has a mean, 0 as mean and 1 as standard deviation. And you can see that like you are not far from each value. So those values are not far from each other. So this is scaling that you have been using as before. Here I have just created like X data, for example, this data X, and then I have used these two methods, the min max methods and the standard deviation, the standardization methods to scale my X. And after doing that, I put them in a data frame. Okay, where I have to okay put together the min max that I have here and the standardization one I have here, and you realize here this is my X. Okay, as you can see, these are the values I have here. 1, for example, here I have 8 and I have 9 here, you know. So when I apply this function, when I try to scale it, the min max here, you can see that everything here is between 0 and 1, for example. Everything is between 0 and 1. So these values are not now far from each other. All right. So any question on feature scaling? So I hope you guys you understand this already and you have been using it.
Question.
If not, all right.
Question, sir.
Yeah, please go ahead, Janet.
What may be the reason why someone can choose to use min max over standard scale?
So I think so. There is no the difference of the choice of this. Sometimes, okay, you might be sometimes maybe required to use min max depending on the data. For example, if maybe you check the minimum and the maximum value, and depending on the like the range you have there, from there the difference, you might maybe try to use min max, or maybe uh, the standardization one. But the main idea here is sometimes, whether you use min max or standardization one, so it's okay, but sometimes it depends on the data, right? It depends on the, for example, let me give you an example. When dealing with missing values, sometimes you use, for example, mean to fill missing values, and sometimes you use median to fill missing values. It depends on like how much missing values you have within your data. But it's not like really sometimes a big deal if you don't have so many missing values to use either maybe mean or median one. So here I think it is sometimes, mostly it is up to you to decide which one to use, right? Depending on the data you have. I don't know if you, as you can see here, I have used both of them, so I don't have the same values, but just the idea behind is to make these values closer, to like to have the same, for example, to follow the same distribution, or to be like between 0 and 1, and then you can fit your model. So I don't know if I have answered your question. So these are just some methods, right? Of course, maybe there's some situation where maybe it's more preferable to use min max depending on the what you have like minimum and what you have as maximum, for example, or you can just use the standardization one. It depends on like on you and also the kind of data you have. Hello, Janet.
Yes, thank you, I get.
Okay, here we have, let us move on to the feature construction. Feature construction, okay. Here I will just talk about binding. For example, you have numerical variables and you want to make it to be categorical variables. You have to create some binds, some beans, for example, and then you can use encoding to encode the beans, for example. That's the main idea here, feature constructions, right? Okay, here what I have loaded this data, height data. Here we have like the height here, the height variables here. So I want to make it into beans, for example. So I have in pandas, you just have this function, pandas.cat, that makes things for you. You have just to specify the number of beans, all right, and then it makes for you. So this is the height, but now you realize that I have like 4 beans, for example. These are the intervals, and this value belongs to this interval, this value belongs to this interval, this value belongs to this interval, and then you can consider these new variables, and you can do some kind of encoding to make it now categorical variables. So this is the main idea behind. You have numerical features, you want to make it categorical features. For example, this is continuous, for example, features, right? You want to make it categorical, you do some kind of binding, you create beans, and you have this data into different intervals, and you use encoding, and then you have categorical variables. And you know that 0 maybe refers to the interval AB, and 1 refers to the interval BC, and then 2 refers to the interval CD. This is like the main idea behind binding, which is feature construction. So you take the feature and you try to do some kind of constructions. You create another feature, but based on the feature you already have, right? From numerical feature, from continuous numerical features to categorical features. So it's possible. You have numerical features or continuous features. You want to make them to be categorical features. So it's possible. Try to do some kind of binding, and then later you do some kind of encoding. So any question on that? Okay, and lastly here, let's talk about feature reduction. And here I use a principal component analysis that also you already know and you have already been using probably for your the past challenges. Okay, and I'm using this Boston housing data. Okay, so basically principal component analysis, what it does is that it just take out like the most relevant, or it just shows you the most relevant features that you have, the most relevant components that you have within your data, because maybe all those components are not relevant for the data for you, for your analysis. Okay, principal components analysis just tries to tell you which components are relevant for you by giving you like the explained variance. The explained variance means like how much variance, like how much information these components have about my target variables. So that's it. Okay, so this is my data. Also, before fitting the PCA, I have to separate the target and the explanatory variables. Okay, I have to fit my PCA on the explanatory variable, for example, right? Okay, this is my the target variable is this, which is a price variable, MDV. So I have just to remove it from there. So this is my explanatory, my feature matrix, for example, my feature variables here. And then I have to scale it as I just said above. Okay, here I only have numerical features. Okay, I have to scale them. If I do not have, for example, numerical feature, let's say I had, for example, something like gender. Okay, male, female. So I have to use encode to encode that variable and to scale that variable. So it's always a good idea whenever you have numerical features to scale it before you fit any kind of like algorithm or models, right? Okay, and then I transform it to be for it to be a data frame. So here I have just dropped the NAs in case that they have some missing values. All right. So this part is very important. When you want to apply PCA, it says that you should split the data into training and testing data. You know, it is important to note at this point, I'm sorry for the background noise, that PCA should not be made to run on the entire data set, right? And this would cause the data to leak, thus causing overfitting. We should not perform also PCA on the training set and the test set separately. Like you have to use the training set to fit the PCA, and the same PCA you use for the training set, you train on the training set, maybe you can use it to just transform your test set to make it now to be like in the form of principal components, right? This is what it is trying to say here.
Hello. Hello.
Yeah.
Hello.
Yeah, I can hear you.
Please, can you go over that? Can you go over the last point? Like you said, we shouldn't fit PCA on the training and test. Can you go over it, please? I didn't quite get it.
Okay. Here, it is important to note at this point that PCA should not be made to run on the entire dataset. And as this would cause the dataset to leak, thus causing overfitting. We should not perform PCA on the train and test separately, as the level of variance will be different in both these datasets, right? So what I mean here is, after you split your data, it's not a good idea to use PCA on the test set and separately you again use PCA on the test set, on the the test set, the training and the test set, you use separately PCA. That's what it's trying to say. Like the PCA used on the training set, it should be the same PCA that you will use for the test set. It's like you fit your model on the training set. It's like you fit your model on the training set. You will use the same model for the test set. Like the test set, you will not just create another model for the test set. No, you cannot just initialize another model for the test set. So this is the same idea. Instead of, okay, for the test set, I have to initialize the PCA to train my PCA to fit my PCA on the training set. So instead of doing the same process, like to repeat the same process fit this over for the test set and fit a new PCA for the test set. What is trying to say that just understand this as the same way when you are fitting a model. You have the training data and you have the tested data. You train your model on the training data, and the model you have trained on the training data, it's the same model that you're going to use for the tested data. So this is the same idea here. You cannot just use this model, take your model to train it on the test training data, and then for the tested data, you initialize a new model again. So this is the same idea. I don't know if you understand what the point or not.
Okay, if I understand you now, what you're saying is that once we have already fitted the PCA on the trained data, we shouldn't create another PCA, right? We should just transform the text data using the PCA that we
exactly.
Okay, thank you.
Exactly. Yeah, so that's what I mean. You know, sometimes, okay, another question. Okay, I hope you understand it. Sometimes, like, the way I explain might not be clear because of my English, but at least you understand what I'm talking about, okay? So...
Hello.
Yeah.
Hello. Okay, what if
I can hear
before
you.
you split the data now, like, now before you perform the train test split, can you apply PCA on the data set before you do the train test split?
Come again?
Okay, can you hear me? What I'm saying is this: what if you have the data sets like joined together before you apply the train test split? Are you going to apply PCA before you do train test split, or you are going to do train test split and then apply PCA on the training data and then use the same model on the testing data?
Yeah, I said it here. You should not apply the PCA on the... Yeah, it's clear, but I said it here. You cannot apply the PCA on the entire data set before you do the splitting. It is important to note that at this point, that PCA should not be made to run on the entire data set. You see the point? So you have to split the data, and you have to train your PCA on the training. Okay. Okay, here I have just split the data into training and testing data, and here I have to initialize my PCA. And you realize that I have initialized my PCA on the training data, right? You can see that I have initialized my PCA on the training data. And I want to do the same thing for the test data. So this PCA that I have here is the same PCA I will use to transform my test data, right? So this is the PCA I have. So, okay, as from now, at the beginning, I have like 13 variables. When I just remove, all variables are 14 variables. But remember, I removed the target variable, right? So now I have 13 variables. So I initialize my PCA with all the 13 variables, right? And I fit it in my train data, and then I transform it. Right, using the model, the PCA dash model here that I have. Okay, so now that I have fitted my model, I can go and check the variance. Okay, it will tell me like the variance for each component, or the ratio of variance. It's the same. Okay, it depends. It's up to you. For example, okay, and here, what is telling me that is the first component, and by order, it gives you like the first component, like the components that have like more variance, or that have more information than the other components. Okay, here I have this. What is telling me that is like the first component has something like 47% of variance. Like it has 47 of, like it can explain my target variables like at 47% of variance, right? And the second component is like 10%, and the third component, and so on. Now, you might try to fix a threshold. If you say that, okay, if I manage to have like some components that together have 90% of variance, or ratio of variance, okay, I can just consider those components and leave out the rest. Let me give you an example. Okay, here I have, for example, 13 variables. Okay, then I have 13 components, for example. if the first 5 components, combining them together, the ratio of variance, if I combine them and I have something like 95 or 90% of variance, I say, okay, like the first 5 components can explain very well my data, so I don't need the rest. So this is the idea behind, right? And when we combine, when doing so, let's say here we have combined the first 7 components. For example, the component 1 has 45%, the component 2 has, like, let's say 11%, and so on. And we take the first 7 components, and we realize that we have something like 95% of variance. In this case, we might say, okay, instead of just considering all the 13 variables, let me just consider the first 7 components, because the first 7 components has enough information to explain my data, and then you can just leave out the rest of those components. So this is the idea behind. Okay, you can try to visualize this like
Hello.
okay.
Yeah, please. When
Yes.
you talk about explain variance or the columns that can actually explain the data, please can you explain what it means by something that can actually explain the target variable? Because I've tried to read about PCA, and most times I get confused about this explain. Like it can explain it for 7%, 30%. Can you just explain that stuff?
Okay, so what I mean here, for example, if you take the first variable, it has, for example, 47% of variance. Like, okay, just understand it in a way that it has, like, this component has 47% of information on the target variable, which is which is good. You cannot just throw out this variable, because if I say that, okay, from you, I know that, for example, let's say some people wants to know some information about you, and I said, okay, those information that you want to know about this guy, me, I know 47% of those information. Do you think that those people will just leave me? They will just try to discuss with me, and because they know that if I tell them those 47% of those the 47% I have about you in terms of information, it might serve as something like they might have something based on that 47%. So they know already something about you. So that means when fitting a model, and when we consider this first component, just by considering this first component, we already have some information about the target variables, because the first component has 47% of information about the target variables. This is just what we call explain variance. Variance is just you see variance here in terms of information, because we are trying to figure out the components that have the most relevant information about our data, so that when we consider those components, we will be able to understand very well our data based on those components, because they already have some information about our data. But when you consider a component with less variance, explain variance, that means that component does not have much information about the target variables. That means it cannot explain very well the target variables, and it is not useful to fit a model with some variables or some components that cannot explain your target variables, because the idea behind is to use based on some variables. You are trying to predict something, but those variables that you already have, they should serve as like information. They should tell you something about the target variables. That's why you are able to predict now in the future what should be the case, for example, in the next coming month, 2 months, or something like that. So I don't know if you understand the explain variance as this.
Yes, I understand it very well. And that question is this: when can you choose between using number of components and certain threshold? Like you explained, I said, okay, if maybe we have about 90%, you can pick the first 5. And then, sometimes you have number of components, you can set the number of components to be 5, 6, or 7. When can you choose between using number of components and setting a threshold? And we combine both together?
It depends. Most of the time, you can just use all of them. As you can see here, you can just use all of them, and you can know from this curve, like, okay, you can start using, for example, 5, and if I realize that the explain variance I have for those 5 components is 50%. I said, okay, it's not enough for me. Let me add. Then you add till maybe you have something like let's say 95% or 90%. But there is an easier way for you to make it. You can just put all variables that you have, for example, the total number of components that you have, and then you see, for example, even before the curve, you can see it here. Okay, you can say this component, I don't need it. So that means maybe I need less components. Maybe let me consider 12 components. And with 12 components, you realize that this one is not also relevant. Okay, you leave it out. You consider maybe 11 components. With 11 components, even this one is not relevant. Okay, when you come here, for example, somewhere like here, you say, okay, I should consider this one. That means, okay, you start counting from here up to here. It gives you like 7 variables, 7 components, and you say, okay, let me choose those 7 variables. You will have the like by the time this curve will start becoming like constant. For example, here is what it does. This is the explained variance for the first component. What it does is that this is not the explained variance for the second component, but it combines the explained variance for the first component plus the explained variance for the second component, and this is here, you know. And then the third component, it combines this explained variance for the first 2 components with the third component, and you have here. Okay, by the time you reach 7, for example, 7 is somewhere like somewhere here, you already have something like more than 90% of explained variance. You can say, okay, I can stop to 7 components, or okay, maximum I can stop to 8 components, for example. You say, okay, let me just take the first 8 components, because with the first 8 components, I really have the information I need to work on my data. So the number of components that you want to choose, you can do it manually to check what you have and to try to improve it, or you can just first of all set all number of components there, and then based on the explained variance that you have, you can know which component to like the number of components that you should consider as final. I don't know if I have answered the question.
Yeah, thanks very much. Thanks.
Okay, so I have fitted my model here, my PCA, and then I'm just naming this, like I'm just putting the data in terms of component. Okay, the first component is the most relevant component, for example, and I have all the 13 components here, as I told you. Okay, I know that with the first 7 components, I am okay. So next, I can try to just stop here to take from this component to this component, and then to leave out this. Because if you, the thing is, if you like consider those components that are not relevant into your model fitting, they will just add noise. So they'll just reduce the performance of your model. Okay, so you just have to leave them out. Just consider those that have like enough information to explain your data. You have something like 95% of information with the first 7 components. That's okay. You said, okay, let me just consider the first 7 components, because if you add more components, it will make your model more complicated, and then you will maybe have overfitting, something like that. But you can try to consider, the thing is to reduce the number of components, but keep in mind that while reducing the number of components, you should consider those that have the most relevant information. You cannot just pick up any number of components you want to pick. You have to consider those that have the relevant information for you to do the kind of analysis you want to do, right? So I have applied my PCA on the feature matrix. Okay, then here I have, okay, you see, I just consider now the first 7 components, and then I concatenate it with my target variables that I removed. And this is now the data I have. Okay, and this is the trend, the trend data that I have. This is the trend data that I have. You see, so now, like, you want now to as I told you, you split the data. right? You split the data into training and testing data, for example. And here is my the data I have as training. So this is my training data now, for example. After fitting the PCA, this is my training data. Okay, then I just remove again, for example, the target variables. Okay, when I want to fit now my model, I'll fit my model on this one, on this train data now. I'll fit my model on this train data. Okay, and then the PCA that I fitted for the training data, I'll use the same PCA. I'll use the same PCA to transform my test data, as you can see here. So I cannot initialize another PCA for my test data. So the same PCA I use the same PCA now to transform my test data. All right. So I have now my test data. This is the test data. Okay. Now you can fit your model on the training data, and then you can test your model on the test data. I don't know if you get now what I mean. So for the test data, you cannot use, like, you cannot initialize again the PCA. So I just use the PCA that I have already on the training data and use it to transform my test data into principal component analysis, for example, into PCA format. And then I can use my model now. After I train my model on this test training data now, I can use the same model to test it in this test data. I don't know if you get me. Anyway, this is the end of this presentation. If you have question, please ask so that we can maybe discuss this.
Hello.
Yeah.
Okay. While I was doing the last week challenge, I had an issue. You know, we're dealing with this financial stuff. It's a financial data set, and we actually did one auto coding or use pd.getDummies to actually generate some dummy variables. And then we applied PCA on the data set. So my question is this: how can we actually know the columns that are actually very, very important using this PCA stuff? And also another challenge I had was that if we reduce these columns with PCA, there are some columns that have been dummy generated that PCA might not capture. I don't know if you get what I'm saying. Like PCA might not capture. So I don't know, how can we actually avoid this kind of things? Or what can you just say about that stuff?
I don't understand very well your question. Maybe can you just say it again?
Okay, the question I'm asking is this: you know, basically after doing PCA, we generate some important features. So my question is, how can we know those columns that, you know, normally the data set has a name, and when we apply PCA, the PCA names will change. The data set columns will change to maybe PCA 1, 2, 3, and 4. So how can we know the names of those columns that are very, very important? Like for the PCA 1 now, that is the most important principal component. How can we actually know that column that is actually the most important component? I don't know if you get.
Okay, I think there is something like for PCA, the better understanding of PCA would require like to understand the geometrical aspect behind PCA and the mathematics behind PCA, because PCA is doing some kind of transformation, some kind of like rotation, right? So it's not like this PC1 is like it corresponds to exactly one variable. It has done some kind of transformation for that variable. Now, what you are interested in is like not like which variable is you are not now you are not working in terms of variables. You are working in terms of components, because there's some kind of transformation that PCA does on those variables. If you just try to maybe have a look of at the geometrical aspect of the PCA, okay, and here we are not anymore interested in, okay, here what will be the name of the variables here, what will be the name of the variables here, and so on. Okay, you might know it, you can know it, so those components, because as long as I'm using PCA, so I just have components, so I'm like I'm not talking about variables. Of course, PCA has done some kind of transformation for each variables. Now I have components. Okay, now I want to know which component is relevant for my variable, for my analysis. But each component has to do with like one variable because it has done some kind of transformation for that variable. So there is a link, but it's not like exactly this PCA1 should be like the name of some variables exactly. It's not exactly the same variable, because if you look at these values, they are not the same values before I use PCA, for example, here. Yeah, they are not the same values. You can take your time to compare these values because PCA has done some kind of transformation. So this is Python, and there are some built-in functions for PCA. So it just does everything for you. But for me, for you to be able to understand very well PCA, I would really advise you to try to look at the math and the geometry behind PCA.
Okay, thank you very much.
Yeah. But what you should know just is, okay, now the model that I will be using, I will just use this PCA now. It's still like as columns, for example, PCA, PC1, PC2. Now these are the things that I have to use in my model, and I know that these are the most relevant components for my data. So they can actually be like they can actually explain my target variables, and I can fit my model on this, and I can do some kind of prediction because I know that they have enough information to explain the target variable.
Okay. Hello.
Yeah.
Hello. Okay.
Yeah, I can
Sorry
hear
now.
you.
Basically now, let's say we are in an office now, we're in a company, and then we're given a particular data set. How can we actually translate this into the business world? I don't know. Like we have these columns now, like because basically last week on challenge we were told to maybe make some recommendations to the managers on people that they can actually target based on some of their features. Okay, now last week we applied PC on it. So how can we actually recommend or tell the managers if the people they can actually target based on, after we have applied this PCA now, we can actually get the name of the component that is actually very important. So my question is this: how can we actually translate this into the business world? Like, you're working in an organization and then you're given a particular data set and you want to target their customers properly, and then you have applied PCA and you have made predictions on customers that will actually churn or leave or will not leave or will subscribe or will not subscribe. So how can you actually relate that into the business world? That's just my main question.
Okay, I think one thing that you should know, PCA is not just like for future reduction. For example, you can still use the same PCA to maybe do some kind of future ranking. For example, for you to select the most important features, which is different from what I'm doing now. Okay, for example, okay, let's say you can use random forest to do future ranking, for example, to know the most important features. But those most important features will not give you, for example, the explain variance of each features. You just plot, okay, and you will see like the most important features. Like maybe the most one will be like the bar will be like higher and so on. So actually, you can use PCA to know the most relevant features within your data without talking about this PC1, PC2, PC. You can just use PCA as random forest to know the most important features within your data. And those features actually normally they should correspond to the most relevant component when using now PCA to reduce the dimension of your data. I don't know if you understand me.
Yes.
Okay.
Thank you very much.
For this one we are using, it doesn't care. It's just doing some kind of transformation on the variables. We don't know. Actually, we don't know if this PC1 was the first variable or the second variable. What we know is that like it is just relevant for us, and it has the most like it has 47% of information, which is the biggest number here. and it is relevant for us. You can use PCA to do some kind of future ranking, like to know the most important
Thank you very
variable.
much.
Okay, you get what I mean? Okay, question?
Yes. Oh, sorry. Last question. I don't know. Last question, please.
Okay.
Last question, please. Can I ask? Sorry that I'm disturbing.
Yeah.
Just want to
Don't worry.
understand.
Yeah,
Last question,
no,
please.
don't worry. You can ask. Don't worry.
Hello.
Yeah,
Can you hear
I can
me?
hear you. Yeah. I
Hello.
can hear you. Yeah, I can hear you. I can hear
Okay.
you.
Okay. The last question is this. Basically, now, last week we deployed models online, like we can use. Okay. Okay. Last 2 weeks. Okay. Last 2 weeks we deployed some models online.
Yeah.
Hello.
Yeah, I can hear you. The line
Can
is
I
cutting,
continue?
but yeah, you can continue. I can hear you.
Okay. So last week we deployed some models online.
Yeah.
Yeah. So last 2 weeks we deployed some models online using either Streamlit or any of these models. So now, if you are to get on another data set, like, or there's an input now, does that mean our model will actually perform another dimensional reduction before it makes any prediction? Take for instance, you have a particular column where people can actually input, like managers that can actually input, like the features that they want to predict for. So does that mean behind now we should have something that can actually convert this and reduce the dimension before it makes prediction? I don't know if my question is clear.
Yeah, I think it's always advisable.
Hello?
Yeah, can you hear me? Can you hear me? Can you hear me? Hello? Hello?
Yes.
Can you hear me?
Yes.
Okay.
Yes.
So
Yes.
I'm saying that it's always advisable to reduce the dimension of the data. Right? Hello? Can you hear me, guys?
Yes, we can hear you.
Okay, I'm saying that it's always advisable.
Yes.
It's always advisable to reduce the dimension of the data if possible, because it's not like a good idea to just leave there some variables that are not relevant for you or some components that are not relevant for you. So dimensionality reduction, I think, so you can even do it without knowing it, because whenever you are fitting a model, you cannot just consider all variables. By selecting some variables, you are doing some kind of dimensionality reduction, because you can, those variables that are not relevant for your feature, for your model, if you want, you can just try to throw them, for example. But in terms of business, there are some variables not relevant. Even if they're not relevant, it's always advisable to do some kind of dimensionality reduction when you have a data. So it's not like only for, I don't know, model deployment, something like that. Anytime it's advisable to reduce, to not consider all variables. I don't know if you understand me.
Yes. Thank you very much. Yeah.
You
Thank you
don't.
very much.
All right. Yeah, someone is asking if I can upload this file. Yeah, of course, I will upload it right after the presentation. Features should we start considering? Yeah, I think I talk about this. So you can start with the total number of features you have as the total as the number of components, and then you based on the explained variance and based on the that curve you have here, based on the, okay, let's say I consider the total number of variables variables I have from 0 explain variance you have here, you realize that at the point where you already have something like more than 90% of information of variance, so you can stop from there if you want. Yeah, you can stop from there, or maybe
that
you
was
can
what
start.
the question was asking. Like it was asking,
Okay,
like if you have like one number of features, like on your data set, how many features do you need to have before you start considering PCA?
If you have data with very large number of features, you can just think about PCA. Yeah, you can think about PCA. And even if with, like, for example, with 5 variables, you can still try to apply PCA. Maybe among those 5 variables, maybe two of them, or maybe only 2 variables are relevant, or 2 components are relevant for you. So, but most of the time, PCA is when you have made like so many variables and you are sure that most of these variables are not relevant for you, you can just apply PCA. But I think there is no specific number of features with which you should start considering PCA. I don't think so. PCA is just a way for you to extract the most relevant components for you. That's all. Did I answer the question? All right. So, okay. If you don't have question, I think I will just upload this in the and you will have access. And also, what I would advise, in the job, because this is like the impact of it and to know anything. So it has just done those kind of steps for you. But you should understand the theory, the theory behind PCA. I would advise to really go and read the theory behind PCA, because PCA is actually very important. 6 months internship, data science internship in the Center for Radio Astronomy in Rhodes University, for example, in Grahamstown in South Africa. Okay, I was working on radio astronomy data, and those data, I cannot even tell you the number of features they have. But I use PCA and SVD as a way to reduce the dimension of the data, and it works very well. It worked very well. It worked even better than the method they have been using to reduce the dimension of the data. So PCA actually is very important when dealing with when doing data analysis, and you want to reduce the dimension of the data. You want to extract the most relevant component for your data, and then based on those components, you can use do some kind of fit some kind of model, something like that. Exactly, Emmanuel, truncated SVD. Exactly, I use truncated SVD and PCA, and even random projection as a way to reduce the dimension of the data with radio astronomy data. Those data are very, very, very big.
Hello. Hello.
Yeah.
Hello. Hello.
Yeah, I can hear you.
Yeah, I know the session is almost over, but please, I have a question. I'm very sorry.
I can hear you. Yeah, I can hear you.
Yeah, you talk about SVD, and you said something like.
Yeah.
Yeah, you talk about SVD. So basically, so you said you applied SVD after applying PCA.
Yeah.
Like, why? Is that can SVD alone be sufficient, or we need to apply it after applying PCA?
Of course, you can just apply SVD alone as just SVD is singular value decomposition. So actually, you have your matrix, you have your data, and you just consider your data as a matrix. All right. So you compute the agent values of the matrix A transpose, for example. You take that agent values, and you compute the agent vectors, and then you compute the corresponding agent values, right? And PCA, we are talking about the most relevant components. In SVD, for example, truncated SVD, you just consider the biggest singular values. Okay, you just consider the biggest singular values, and then you leave out the rest. And each singular values corresponds to one particular variables. All right. So if you consider these singular values, that means you have to consider that corresponding variables. That means that that variable is relevant for you, and you have to consider it. And you go to the next. The second singular values will correspond to another variable. If that singular values is is big, if the number is significant, then you have to consider. That means that the corresponding variable also is significant for you. Then for those singular values that are almost equal to 0, you can just leave them out. That's why we call it truncated SVD, as Emmanuel just mentioned. So SVD is just singular value decomposition. It's like some kind of, that's why I'm telling you that SVD and principal component analysis, because you cannot understand SVD without understanding those kind of the manipulation behind those kind of matrices. You have to understand very well matrices, how to work, how to manipulate matrices, transpose, inverse, all those kind of things, how to compute determinant of a matrix, how to compute the agent vectors of the matrix, how to compute agent values of the matrix, all those kind of things. But Python does everything for you. That's why if you are just limited to Python, you might not really understand like the main idea behind the theory behind SVD or the theory behind principal component analysis. So it's the same. And from PCA, I guess you can have SVD, for example, or I think it's from SVD that you can have PCA. But it's not like if you apply PCA, then you have to apply SVD. No, you can do them separately. Me, for example, that work, I mainly use, for example, SVD. I use PCA, but I mainly use SVD because it depends. The kind of data I have, SVD was more appropriate for me to use, and I got very nice results. Better than the way they have been using, like the way they have been compressing their data. For example, I could share with you the report of that internship. So I just use SVD to reduce the dimension of the data, and those data, the dimension is super big. Yeah, thank you very much. And as I said, I really advise you to try to understand the theory behind SVD and PCA. They are very important in data analysis and in dimensionality reduction. Okay, question? Anyway, feel free. We can discuss this in the Slack channels. You can reach out to me privately if you want. Or yeah, if you have questions right now, you can still ask.
File, please.
Huh? Come again? You know? Okay, if you don't have any more questions, guys, so I think we have to end this presentation. I know that you are working on your.
I think my network is bad too.
Yeah. Hello.
I think can you just share with me some materials on PC and SVD and also the file for that your internship?
Okay, don't worry. I will share that report with you guys, and then I will upload this file right away after this presentation. I will upload this file. Don't worry.